Dynamics Days workshop, because James and I organized a workshop on the same topic with many of the same speakers at the SciM Life Sciences meeting, which was then canceled. And then we signed up to do the Dynamics Days, and then it was uncanceled, the Life Sciences, and moved online. So as a co-organizer, I told everybody it was fine to give the same talk twice under the circumstances. In my case, the first half of the talk is the same and the second half is different. So I may zoom through the first half. Also, I didn't realize it was only 20 minutes instead of closer to 30. So I'll cut out some material in the middle, and if people have questions, I can go back to whatever I shouldn't have skipped. So tell me when it's time to actually start.
Yep, let's start now. It's 10:10.
Okay, great. So this is a talk about phase reduction for stochastic oscillators, and I know the other speakers are familiar with the questions motivating this stuff, and many of you were at the SciM Life Sciences workshop on the same topic. So I'm going to skip some of the preliminary stuff, which just says what we're doing with phase reduction is we're trying to find a lower dimensional representation of a higher dimensional phenomenon that still keeps the essential properties. And I'm going to take for granted that everybody appreciates the importance of oscillations in neuroscience and mathematical biology and beyond, and also stochastic oscillations. I'm also going to assume that people are pretty much familiar with the basic notion of phase reduction. So if you've got a nonlinear dynamical system that has a limit cycle, then you might have something like in this picture with this neural model, the Morris-Lacar model. And if you change coordinates so that you introduce a coordinate system where this one-dimensional phase representation is advancing at a constant rate, then if you compare, say, the voltage versus the phase trajectories, the one is advancing in sort of fits and starts, and the other is constantly moving at the same velocity, except because it's periodic, you have to then reset it every time you go around the circle. So what we'd like to do is something similar for stochastic oscillators, and also to develop the related notion of isochrons. You see a nice picture of isochrons here. But things are complicated by the fact that the systems are noisy. So before I explain those complications, I'll point out that there are two ways of defining isochrons that go back to Guggenheimer's classic paper, 1975. You could ask for the set of initial conditions that all behave the same way over long times. So that would be like finding the set of points that all converge in common to a single trajectory along the isochron without any lag or phase shift. The other definition is to ask for a surface or a family of surfaces of Poincare sections with the property that any leaf in that family moves along together. And in particular, if you look at where one leaf is one period later, it's back as a subset of the same leaf. These two ways of defining phase or isochrons are equivalent when you have ordinary differential equations, but they lead to two different approaches in the literature for stochastic differential equations. All right, so both of these approaches break down when things are noisy, because on the one hand, if you're looking at what trajectories do in the long term, well, nothing is really periodic anymore, so nothing converges to anything else. At least if every trajectory has different noise, that's true. Also, if you put down any surface and you ask for the time it takes to go around once and come back to that surface, that's going to be a random variable. And so it's not going to be exactly the same every time. All right, so there's been several suggestions in the literature for how to extend the notion of phase to noisy oscillators. And two that I'm particularly familiar with, but that doesn't exhaust them, are the mean return time construction and then the asymptotic phase from diagonalizing the operator that tells you how the densities evolve. The second thing, the operator theoretic approach, is what I talked about at the SciM Life Sciences conference, so I'm going to skip it. And instead, I'll talk about the mean return time isochrons. And this is essentially work that came out earlier this year with Alex Kao, Thomas Lindner, and myself. We have a paper in the Science Journal of Applied Mathematics. There's also new results, if I can squeeze them in at the end of my 20 minutes, where my current graduate student, Shusen Pu, and I have been extending this to get at the variance of interspike intervals. So hopefully I'll have time to say a little bit about that. All right, so I'm going to focus on the mean return time idea. The setup formally here is easiest to describe in the case where we have a stochastic differential equation driven by a Wiener process. So A of x is my deterministic vector field, B of x is my, fancy B of x is my noise coefficients, and we use the Ito interpretation if we need to. Okay, so then I take BB transpose to get a new matrix B, a square matrix B, and I can think about how the density of trajectories evolves. And I have two operators that emerge. What I call the forward operator, or the Kolmogorov operator, tells me how densities move forwards in time. And then the backward operator is the adjoint, the formal adjoint of the forward operator. It's also called the generator of the Markov process. And it tells you how an observable evolves on average forward in time. So one operator describes the densities, the other describes observables. The backwards operator is also closely related to the Koopman operator, or in some contexts identical to the Koopman operator. Okay, so this idea of extending phase description to noisy oscillators using isochrons originates with Schwab et al. And Pekovsky's paper, where they said, now I wish I had a little pointer here. You know what? I wonder if there's a way under annotate. Can I get a mouse? No, okay. I'm not going to try to figure that out here. It's, oh, there's the spotlight command. Maybe that's what I want. Okay. And that also didn't, okay, so I will, oops, I'll try to get control of my mouse again here. This is a disaster. There we go. All right. So if you look at the red curve on the left bottom panel and the green curve, these are two Poincare sections that are both candidate isochron sections. And what Schwab et al. And Pekovsky did was they began a large ensemble of trajectories starting at each of these different points, and they looked for the average time at which you return, having gone around once, you return to that section. And with the little inset plot, you can see that the green curve gives a roughly constant return times, and the red curve doesn't. And so the green curve would be a mean return time isochron. They developed a numerical procedure that involves many repetitions of ensembles and adjusting the knots in a spline representation of the little curves until you get more or less constant mean return times. This is a very tedious procedure. When I talked to Eustace about it, he swore he would never touch anything like this again because it cost him too many years of his life to get it to run. So what Benjamin Lindner and I thought about was, well, maybe we can describe these curves in a different way. And what we try to do is to come up with a partial differential equations description to capture the same curves. So the example system I'll use here is a heteroclinic oscillator. So in the absence of noise, this vector field, so if I set D to 0, this vector field gives me a system that spirals around and around with a diverging period. And so it's a heteroclinic, stable heteroclinic cycle or attracting heteroclinic orbits. If I add a little bit of noise, then I get something that acts like an oscillator. So this is a situation that's interesting because I cannot refer to the underlying deterministic oscillators isochrons and somehow perturb off of them to look at the effects of noise because there isn't any underlying deterministic oscillator. If I turn the noise off, then I don't have finite period oscillations at all. Nevertheless, it does act like an oscillator when the noise is present. Here, Benjamin and I have a paper where we calculated the power spectrum. It's tricky since it's a nonlinear stochastic dynamical system, but we were able to do it. And so you see there's a nice peak in the power spectrum, and it really does act like an oscillator. Okay, so we know that if I take a stochastic process and I ask how long does it take to reach some location, some set, say part of the wall here, then I can set that up as a first passage time problem. And the first passage time function, so that's the mean time it takes to get from a starting point x to the to an escape point on the boundary. That's an observable that evolves at a constant rate of -1, because the time left on average until something happens is a random variable that is always decreasing on average at rate 1, just by definition, because the clock is just counting down until the absorption happens. So L dagger acting on t equals -1, that's the operator, the non-homogeneous operator we have that governs the mean first passage time. The first passage time is 0 if you start at the wall, and everywhere else we have adjoint reflecting boundary conditions. And the problem is we would like to establish an isochron, which is a surface where if I start at that isochron, I go all the way around once, and then I come back with the same mean time, no matter where I started. Now, there's a bit of a problem here, because if I'm starting on that isochron, then the time it takes me to go around, well, the time it takes to hit that isochron is 0, because I'm starting there. So we had to finesse that by imposing a jump condition equal to the mean period and keeping track of whether you've gone around once or not. You can think of it as unwrapping the surface like a water slide. You know, you're at the same location, but you're one rotation lower. And so you can basically set the PDE up on this extended domain, and then everything makes sense. So in our paper, we go through the formalities of this, and I'll skip, for the sake of time, I'll skip the various assumptions which involve having a strongly elliptic second order operator and writing down the boundary conditions a certain way, and the probability current should actually be moving instead of not moving. You can read the paper to see the various assumptions and details, and the proof. The gist of the paper is we prove existence and uniqueness of a function whose level curves satisfy these properties and give us the isochrons. So I'm going to skip ahead just to show an example. This is for the heteroclinic oscillator again. So we can write down the backward operator, the generator. We can set up the non-homogeneous equation, L dagger t equals -1. We impose a jump by the mean period and adjoint reflecting boundary conditions where you see the red boundaries. The jump is occurring across the blue boundary. And the interesting thing is it doesn't matter where you put the cut, where you put the jump. You get the same isochrons regardless. So that's a nice property of the system. And then on the right, you see the mean return time isochrons calculated as the solution of the PDE. And instead of taking 2 years to debug and get this to work for poor Eustace, you know, this runs in like under a minute on a standard laptop, just with MATLAB. So the blue dashed curve, the blue dotted curve is one of these isochronal sections. The red is just an arbitrary spoke of the wheel section. And you can do the mean return time experiment, and you see that if you take the spoke of a wheel, you have very non-uniform mean return times. But if you use the isochron, then you get, it has the mean return time property. So that's all great news. And now I have, 5 more minutes. So that's the old stuff that was published. And now the unpublished stuff, which I'm very excited about. So if you are interested in noisy systems because you're interested in noisy nerve cells, one of the classic problems is to calculate the variance of the interspike interval. How variable is the firing time of a cell if you just drive it and its firing is perturbed by ion channel noise? Well, we've applied this mean return time isochron setup to that problem in the Hodgkin-Huxley system. So our underlying channel model, or our underlying Hodgkin-Huxley model, is a Markov model where you're probably familiar with these states. So the potassium channel has got 5 states, the last of which is open and conducting. The sodium channel has got 8 states with 20 directed arrows representing the different transitions between them. We developed a Langevin model for this system, which is where each of the 28 different arrows gets its own independent white noise term. And that's an interesting story. We have a paper that just appeared, or is just coming out in neural computation on that. Okay, but what we want to do with it here is calculate the mean return time between one isochron and coming back to that same isochron, which gives us an approximation of the interspike interval. Okay, so here's the same setup as before, we choose a mean return time isochron, and the first passage time, tau, from an arbitrary starting point to that isochron is called tau. The first moment we call t, same as before. It obeys the same equation, L dagger t equals -1. The second moment, which we need to get the variance, is just the expected value of tau squared, and it satisfies, and you can look it up in Gardner, L dagger of s is minus twice the mean time from x. So the variability of timing just sort of accumulates at a constant rate in time as you move towards the isochron. Dinkin's formula tells you how the expected value of an observable evolves in time, and it involves the same generator, the same backward operator. And so if we plug in the variance function for the observable, then if we do a small noise expansion, we can get a result where in the limit of small noise, the variance of the return time from one isochron to the next decomposes into a sum of directed edges in this graph. So each of the 28 edges in this graph gives its own contribution to the variance. All right, time is short, so I won't spend as much time as I ought to on this formula. Essentially what you do is you integrate once around the deterministic limit cycle. So for the Hodgkin-Huxley system, unlike the heteroclinic oscillator, there is a deterministic limit cycle. Z is the phase response curve, the classic infinitesimal phase response curve, which tells you the sensitivity of timing to small perturbations near the limit cycle. Zeta k is the stoichiometry vector. So in this kind of master equation setup, each of the edges carries its own stoichiometry vector. Alpha is the transition rate per capita, voltage dependent along the kth edge in that transition graph, and Q is the mean number of channels in each state. So we have an expression, we can calculate it semi-analytically or numerically, and here's the results. It's gorgeous. So what we've got here is the variance of the interspike interval based on the voltage crossing, using the voltage when you cross a certain voltage to count when the spike happens, as a function of the strength of the noise. So we have a parameter, the inverse system size, that governs the strength of the noise. And so we can make our system less noisy or more noisy by effectively including more channels or fewer channels. So if we make it not very noisy, then you get this beautiful linear dependence where the variability of the interspike interval just grows linearly with the noise. And it respects this sum where each edge contributes makes its own contribution. So then you can do something that we call stochastic shielding, where you just look at the effect of one edge or another edge, take them apart, put them back together again, and that's where you get all of these different curves all growing with the same slope. This linear decomposition is good up to the point where the dash curve deviates from the red and black curves, which is, the noise has to be fairly small. And here's a closer look at that. And so for the low noise case, we compared both the return time for an isochron and the return time from a spike section. And the reason that this is important to compare is because when you count the interspike interval based on a spike defined as when you cross a certain voltage during the rising phase of a voltage spike, that surface in your state space is not an isochron. And in fact, we discovered, to our surprise, that the variance of the time between spikes depends on where you set the voltage to trigger identifying a spike. If you make the voltage higher, you get a larger variance. And if you make the voltage lower, closer to the threshold for spiking, you get a lower variance. And I do not completely understand why the dependency goes that direction, but this is robust. We see this not only in numerical simulations, but in data recorded from the laboratory. So my collaborator records spiking of Purkinje cells recorded in slice, and you take a data set and you set a voltage threshold to count the spikes. And if you change the voltage from higher to lower, of course, you get the same number of spikes, and so the average interspike interval is the same, but the variance of the interspike interval changes. It only changes a little bit, but it definitely changes. And so in the lower plot, you see the black curve is the interspike interval defined not in terms of voltage, but in terms of the phase variable. And the gray curve is the interspike interval defined in terms of different voltage thresholds. And that uses up my time. So I'm gonna, okay, there's some open questions about what these different notions of phase are good for, but I'll stop here because it'd be great to have a little discussion.
Thanks, Peter. So if you please, if you have any questions, raise your hand or write them in the chat. I have a quick question to kick things off. You said that it was the Hodgkin-Huxley with an oscillation, right? So it's...
Yeah, there's a driving, right, we impose a fixed driving current so that it is, the deterministic system has a nice limit cycle.
So could you use the same analysis when it doesn't have the driving current? So it's like a stable fixed point?
You can certainly write down the generator of the process. That's no problem. The asymptotics that we use to derive the variance of the return time require there to be a limit cycle if you have zero noise, and then because we do a perturbative expansion in small noise. So here this function t that gives the level curves of which give the isochrons, when the noise is turned off, this is just the asymptotic phase function for the deterministic system. That would be T0.
Mm-hmm. Mm-hmm.
And so if you had an excitable system that was noise dependent, as we did with the heteroclinic oscillator system, then you can calculate everything, but not perturbatively. You'd have to solve the PDE and with the right boundary conditions. And you're starting in a 4-dimensional. So for Hodgkin-Huxley, for the classic Hodgkin-Huxley ODE system, you'd be starting with a minimum 4 dimensions. So you'd be solving a PDE in a 4-dimensional space, or possibly in a 14-dimensional space if you include the entire channel. If you include the entire channel state structure, you need more like 12 or 14 dimensions. So I don't know how to solve a PDE numerically in that many dimensions.
Yeah, probably very hard.
So that would be a limitation.
Yeah.
Conceptually, yes. There's no obstacle to.
And so it was like what was Fitz-Inuguma? Would that be a lot easier?
Yeah, Fitz-Inuguma or the 2-dimensional Morris-Lacar, maybe even the 3-dimensional Morris-Lacar. Or if you take the Hodgkin-Huxley system and you recognize that it converges quickly to a low-dimensional manifold, and you parameterize that manifold, then you could make a lower dimensional representation of it.
Mm-hmm. Oh, that's very interesting. Any other questions?
I have a question. I can't figure out how to raise my hand. I don't know if that's a Zoom feature.
Yeah, just speak. It's all right.
Okay. Peter, from reading the K.O. Lindner-Thomas paper, and I guess seeing one of the figures in your talk, my impression is that when you set up the PDE and solve it, whatever the stability basin might be, you kind of take a compact piece of it, an annular region, and you set up a reflecting boundary there. And I guess my main question about that is, does the choice of reflecting boundary affect the isochrons that you get? And then a related follow-up question is, in the deterministic case, in the entire stability basin, you have isochrons. In the stochastic case, in your paper, you kind of take this like compact piece, this annular region with a nice solid region with a boundary. And I'm wondering, is there any way to set up a PD for, I don't know if the stability Bayesian quite makes sense in the stochastic case, but I'm wondering if there's any way to set this up without taking a compact piece of the oscillating region?
Okay, so for this specific system here, and then I'll go to the more general question. The stochastic differential equation for the heteroclinic oscillator is defined in a compact domain to begin with. That is to say, the outer boundary is already built into the problem. The inner boundary, is the little square that's poked out in the middle, that you have to pull out for numerical reasons because all the isochrons converge there and you're trying to resolve something that is discontinuous. We looked at changing the size of that inner core, and in the supplement to the paper, we show that the isochrons don't change. I mean, they change right at the core if you're changing the core, but changing the core doesn't change them elsewhere. And the reason qualitatively is because the stationary probability for the system is concentrated on the outside. So if you run the thing for a long time, most of the probability, there's almost no, the chance of being in a small neighborhood of the middle is very, very small. And that's why there's not, changing that inner boundary doesn't have much effect. For the more general question, if you've got a system that has a stationary distribution, then if you go far enough away from the stationary distribution, then you'll be in a region with very low density. And what I think happens is that you can put a reflecting boundary around that to make it compact without really changing the structure of the isochron, the true isochrons versus the numerical ones, as long as you're not cutting through a part of the region that has significant density. A more satisfying answer would be to make a change of coordinates where you sort of compactify stuff out at infinity and put your process, make a new process on a compact domain that, like the Poincare sphere or something. I haven't tried doing that. I don't know what that would look like.
Great, thank you. Thanks, Peter. I think we better move to Zara, and maybe we can chat after.
Okay, thanks for the questions.
Please make her host. Thank you. Make Zara host.
I can make Zara the host. So, okay, let me get out of my, stop share, participants, here we go. Whoops, and I can make Zara make host. Okay, Zara, you are now the host.